In this presentation, we will show how mass can be created by additional, potentially compactified dimensions. For this, we are going to apply what we think is a so-called theory of everything approach. It is widely assumed that Einstein's general theory of relativity cannot be combined with quantum theory. At least, so far, nobody has found a truly conclusive way. In this presentation, it will be shown that the job was in principle already done by no other than the German mathematician David Hilbert. There is no need to combine quantum theory and general theory of relativity because the latter already contains the first, and mass creation is possible via the entanglement with additional dimensions. A theory of everything, for which we are aiming here, should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In this presentation, we will concentrate on the metric derivation of the Klein-Gordon equation and mass as one of the essential parameters in this very equation. From there, it is simple to also extract the metric appearance of mass for Dirac, see part 3 of this series, Schrödinger, part 4, and other quantum equations. Our starting point is the so-called Einstein-Hilbert action, a variational integral based on a Hamilton extremal principle. Already in 1915, it was the great German mathematician David Hilbert who derived Einstein's field equations from such a fundamental minimum principle. What Hilbert apparently did not see was that his formula, in fact, contained much more than just the Einstein field equations, but he had also found the fundament for quantum theory. In this presentation, we will now show what Hilbert had missed, or, taking Hilbert's genius, perhaps simply not considered important enough to be mentioned at all. As we have already shown in an earlier presentation, see part 1 of our little series, that we do not need the matter term Lm nor a cosmological constant to obtain matter, we set both lambda and Lm equal to 0 and just proceed with the curvature of spacetime, known as the Ricci scalar, as the kernel within our variation. Now, by following Hilbert's classical derivation, we obtain the so-called vacuum Einstein field equations. Things change, however, in a rather interesting manner when introducing a slightly adapted metric tensor with a scaling factor as shown here. Hilbert's variation then yields a much more complex kernel. This kernel can dramatically be simplified by demanding the scaling function to fulfill a special condition. Now we split up the variated contravariant metric tensor into its scaling and its tensor part as shown here. As a result, we obtain two equations, a scalar and a tensor one. In this presentation, we ignore the tensor equation, for example by simply assuming that the variation of the metric tensor gives 0 or is so small that we can assume it to vanish against the scalar part. Then we intend to fulfill the scalar, which is to say the first equation, by demanding the kernel of the integral to be equal to 0. This gives us a very simple partial differential equation, and by inserting our setting for the scaling function f, we clearly recognize a similarity to the Klein-Gordon equation. Now we have two options to incorporate mass. In part 2 of this series, we have already shown the possibility of finding this term within the Ricci curvature R. Thereby we assumed a Minkowski-like spacetime and split up the Laplace operator into its time derivative and its spatial part. Subsequent comparison with the classical Klein-Gordon equation from the beginning of our presentation then shows us that we indeed have obtained a relativistic quantum equation directly out of the Einstein-Hilbert action by just applying a scaled metric tensor. We realize that, in our metric generally relativistic theory, the scaling function, which is nothing else but a volume factor, is just equivalent to the quantum theoretical wave function. We also see how the curvature term takes on the function of the classical mass and potential. Another possibility to obtain masses requires the introduction of higher dimensions. Here is just one example in a spacetime with 6 dimensions. The 2 additional dimensions shall be u and v, whereby the 2 are entangled with each other via a coupling function g of v, as shown here. By giving this entanglement function a certain shape and assuming a completely flat spacetime with r equals 0, the Hilbert formalism provides us with a perfect Klein-Gordon quantum equation with mass. Investigation of the function g of v shows us that this function is of bell-like shape and can be arbitrarily compactified. This means that the addition dimensions might not be realized as dimensions, but only occur to us as masses. Not setting r equal to 0, this equation can even be generalized and nicely mirrors the classical Klein-Gordon equation with mass and potential. Thus, we have the possibility to find mass and potential interaction plus other inertia either via additional dimensions or within the Ricci curvature when deriving quantum equations from the Einstein-Hilbert action via the classical Hilbert calculus as shown here. In order to obtain the correct metric equivalence to classical problems like the hydrogen equation with spin, we have already developed models with up to 10 dimensions and more. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out here again, however, that we do not consider us the first to have found the connection. In principle, namely, it all was already inside Hilbert's ingenious approach, and he only could not see it because, at the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and his main goal was the derivation of the Einstein field equations, and thus, as Einstein had not bothered about also finding quantum equations inside his general theory of relativity, Hilbert, as a mathematician, obviously saw no need to consider the broader spectrum residing in his approach. These new insights open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? The optimum is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in this talk. Next smaller step is just the naturalized AI, which still is a small Manhattan project. This too already reaches very far and propels the owner into a global monopolistic and long-time leading position, unless somebody achieves a takeover via a working quantum gravity computer tech. Everything else are service projects.